And I'll live code a simple game here using Yampa. I call the game Yampy Cube, and it would look approximately like this. So, as you can see, it's a very simplified clone of Flappy Bird. And it's kind of simple enough but it also shows some basic concepts of Yampa. And I wouldn't be really starting from scratch, but I have some stuff predefined, which is you can actually clone the code which I have here at the moment from here. And I've pre-written some stuff for rendering the graphics. We're using SDL and for handling the user input. So all what would I have to write now is the game logic. And in imports, I import the Yampa and then some other models which I've already written. And at first I have some constants here, nothing interesting. I'll be just using them throughout. And then we have the game state. Okay, so speaking of the game state, the whole game can be defined with 4 variables basically. We have 2 objects. One object is a cube and another is a pipe. There are 2 pipes, but to define them we only need to talk about one, the bottom one. So we define a cube with its position and its velocity, which can be captured into this Haskell data type. So a cube is defined by its position, which is a double, and velocity. And then pipe is defined by the height of the bottom pipe and the pipe X position. And as this gap is fixed, we can calculate the rest to do the rendering and state calculations. And of course the cube is also fixed on the X value, so it doesn't move left or right, only up and down. And here my whole game logic would be captured inside this game function. And from the type we can see that game has this weird type SF. And SF stands for signal function. And for now I wouldn't be going into detail of what is a signal function, but it would be enough to say that signal function has 2 arguments. The first one is its input and the second one is its output. And signal function describes a behavior of its output, and this behavior can react to its input. So here with these type definitions we say that the game function describes a behavior of a game, and the game can react to application input. And in the definition for now we have this constant initial game state. Note that I defined some initial values here, like initial game state, initial pipe state, initial cube state. And the constant comes from Yampa, and it takes some value and returns a signal function which would always yield that constant value for all times, always. And in the previous talk there was this arrows thing, and in fact arrows is not just something for manipulating functions, it's just an abstraction. And a signal function is implementation of that abstraction. So any signal function is also an arrow, and therefore we can use all the goodies which Haskell provides for arrows and apply them to the signal function. For example, we can use all those combinators like this thing and this thing and these fanouts and ampersands and all this stuff. And more importantly, because these combinators are not very scalable and they're not so convenient to use and to read, we can use the arrow notation. And we can rewrite this constant thing with arrow notation. But first let's just try to run and look what we have at the moment. And at the moment we have just this frame. It's a constant state. There are actually pipes there. You can't see them because they're somewhere here. And what we will do now is that we will first rewrite it with arrow notation, and then we will bring in the pipes into the frame. Just you can make sure that they're there. So, if you...
So this is not changing because you have constant there?
Yes, exactly. I'm just yielding this initial game state value. And constant is kind of signal function creation, which comes from Yampa, but we can as well use arrow notation. And if you remember that the arrow notation is introduced with this proc keyword, which is followed by a variable name to which the signal function input which will be binded to. I'll call it input here. And then we put this arrow, kind of lambda thing, and do keyword. And then here we have an arrow notation block where we can have some bindings. More on that later. And in the end of an arrow notation block, we should have some return value. And we return the value with this return a function, and the value is fed in there with this feeding operator. It's kind of like a mouth. And the value which we feed there is initial game state. And if we compile and run it now, we get the same thing as we had before, because we just replace this constant with an arrow notation. Because in the future we want to extend this game, and the arrow notation allows us to do it more conveniently. And I said that we can have some bindings inside the arrow notation, and the simplest binding, there are actually only two binding forms, pretty much. The simplest one is the let. So we can say let, and then we can put some variable name, for example cube, and an expression which would be binded to that variable name. So now cube equals init cube. Or we can put something like cube with a position, let's say 350, and velocity 0 here. And we can do same for the pipe. And this would be just a pipe. Previously pipe was at width, which is 300. But now let's make it a bit smaller so we can see it. And it would be 250. And the pipe height would be 150, let's say. And now instead of returning initial game, we would be returning a game with this cube and pipe. And we can see that now this updated, the cube went a bit higher and the pipe appeared here. So this was just to demonstrate you that we have this kind of rendering thing, so we can just return this pure game state and then it would be rendered. So we do not have to handle the rendering. I already written that. Okay, and now we want to do something more interesting rather than just the static frames, and let's start with defining our main character, which is a cube. So a cube. And to remind you, the cube state consists of two variables, the position and the velocity. And to get started, now we kind of bind the cube here, but I would want to move it into a separate signal function just to keep things kind of modular. So I'll define a function falling cube, because eventually cube would need to fall down, and it will be a signal function from anything. Let me just write anything here to a game. And notice that this anything is not a concrete, is not any type. We don't have any constraints on it. It's just a type variable. It can be just a as well. And from that, just from this type declaration, we can see that falling cube can't react to anything because it doesn't ask for any specific input. And if it doesn't know anything about its input, it can't make any decisions based on that input. So, and for now, I would just define a falling cube as this old constant thing with init cube, just to first show you how we can use this falling cube inside our game. And what we want to do now is that we want to make use of this falling cube here. We can just try to do something like that. Let cube equals falling cube. And this wouldn't really compile because a type of falling cube is a signal function. But here we bind it to a name cube, and the cube should be of type cube. Also, I made a typo here. It should be not game but cube. Sorry for that. So yeah, and after I fix that, I would have only one type error. So here I would introduce another binding form in arrow notation, which you already saw on previous talk. And this is when we kind of need to run some signal function inside another signal function. That's probably not the right term to run, but it probably explains the thing. And for that, we kind of use this arrow. We say that the cube is binded from falling cube, and the falling cube would be feeded with some input. Again, we use this feeding operator, and I would feed it with input of our game, because although for now it doesn't specify any input, probably we'll change it later, because in the end we want this to react somehow. And if we run it now, again nothing changed, but what we did is just that now our cube logic is moved to a separate function, falling cube. And we can go on and continue with the falling cube. Again, first thing I'll do, because further I would need to define the position and velocity there, and it's much more convenient to do with arrow notation. I'll rewrite it into arrow notation. And oops, like that. And just check that it compiles. Any questions so far? Yeah.
So how does the signal function and the circuit kind of relate to each other? Because the audience is a little bit now familiar with the circuit. What was, for example, a negative AND gate in the previous example, and now the question is how the audience can relate what they already know about the circuits to this signal function, what you have here.
There would be a bit more in-depth explanation of signal function just a little bit later, but the point that, well, in your example, the circuits were just a synonym for functions. So circuits were taking some values and returning some other values, and they didn't have any internal state, but the signal function they actually do have some internal state kind of thing, which is not controlled by us. But you'll see later that they have some superpower, which circuits doesn't have. And okay, now we want to define an actual falling cube, which would be actually falling, and for that we would need a little bit of physics. And these two equations can define the behavior of falling cube. So I'll just read them. We have a velocity, and velocity of time is defined as initial velocity plus the integration of negative gravitational vector and with respect to time. And the position is defined as initial position plus the integral of a velocity with respect to time. Before we go about trying to implement these two equations in code, we lack two things in the scope of our falling cube, namely this initial velocity and initial position. And it would make sense that the falling cube would be taken an initial cube state, so that we would be able to say like something like, hey, give me a falling cube which starts here and then it has a zero velocity, so it would start falling down. Or we can say, give me a falling cube which initiates here and it has upward velocity, so it would go upwards and then go down because it loses its velocity. So let's just pass the cube, the initial cube state, to the falling cube. So the falling cube would be taking this cube and then creating a signal function which describes a falling cube behavior which starts at some initial state. And I'll pattern match on this here. Basically, I kind of expand the cube type into initial position and initial velocity. I'll name that in the same way as we have in our formula. So, and now Believe me or not, but these two formulae can be translated into Haskell like this, with these two lines. And well, let me just first write them and show that they work, and then I'll explain them. So the velocity is an initial velocity plus some cryptic symbols, integral of negative gravity, and a position is an initial position plus some cryptic symbols again, integral of a velocity. And to make this actually work, I would need to pass the initial cube state here, because I forgot to update it. And now I compile it. It actually compiled. Yeah. And if I run it, nothing happens for some.
In a cube.
Oh yeah. Yeah, I found I wrote this v and y and still return an initial cube. I should return the cube with velocity v and with position y and velocity v here. And now it falls, which is cool. Yeah. This one thing where arrow notation really shines, because at first I had it written with normal combinators and it wasn't looking that good. It was still good, but not this good. And just to show you that, remember I'm passing the initial cube state here, so I can change it to anything. Let's say I can have a cube which starts on 150 with some upward velocity. And then I would get a cube which kind of goes up and then starts falling. But let's change it back. Okay, now about these two lines, which somehow magically do all the physics. First, the syntax. You already should be familiar with this operator. So I just feed kind of the negative gravitational constant in there. Then here goes some signal function. And then the result is binded to the variable name v. And pretty much the same on the next line. So what's unexplained here is that thing. So this is signal function composition, or actually it's a composition of signal function with a pure function. But if we just lift it into the signal function ourselves, this v0 plus is a pure function, which just takes some value and adds the v0 to it. And then by putting arrow here, we transform this pure function into a signal function. And then we first have the integral, and then we have this one. So the negative gravity gets fed into the integral, and the integral is defined in Yampa, and what it does is that it takes some value on the input and it integrates it with respect to time. A bit later on how it does it actually. And then after we integrated it, we just add the initial velocity. So, and again, I prefer when it's written this way, because it's just kind of shorter and less letters. And the point here is that to integrate with respect to time, we need to have time somewhere, right? Or either it just pulls them out from some magic. And we do not mention a time anywhere here. Like, there is nothing about time. And from that we can conclude that signal function somehow carries the time inside itself. And I would give you some mental model of how signal function could be defined. It's not how it actually defines, but it provides us a good way to think about it. So signal function has a word signal in there. And a signal is a time varying value. So signal with type A would be a time varying value of type A. How can we express a time varying value? The simplest way would be as a function from time to value. So a signal A is a function from time to A. And now a signal function SF from A to B is a transformation of the signal A to a signal B. So we can write it this way. And now you at least see that the time is inside there. And note that it's a bit different between Yampa and other FRP libraries, but in Yampa we do not operate the actual time variant values, but we mainly operate the transformations of those values. So our bread and butter are signal functions, and the signals are abstracted. We can't really get our hands on signals. They're just somewhere inside there. We can't touch them. But the arrow notation allows us to have this kind of illusion that we can bind a value v to a variable v, and then we can return it somehow. But when the Haskell code compiles, this arrow notation gets desugared because it's just a syntactic sugar. It gets desugared into those combinators like this one and this one and this one. But that thing is much nicer to write than all this stuff. And I'll just comment it out and check that I didn't break anything. So this was for the falling cube, just to remind you what we have at the moment. The cube falls down. But the next thing is that we want this cube to react to the user input. So what we want to is a cube that falls down, and when the user taps a touch screen or presses a button or presses the mouse, the cube starts going up. So what happens here is that when the user clicks, the velocity of a cube gets increased. So, and then it goes up. But in fact, it's still the same falling cube. So here it was falling, and then its velocity got increased, and it's still falling cube, but the velocity is upward, so it goes up, and then it starts falling again, and user probably clicks again. And we want to go it as long as the user doesn't lose. So we would want to define a flappy cube, or flapping cube, let's call it. And it would have pretty much the same type as a falling cube. We have one difference. The resulting signal function would have an application input on its input. Why is that? Because a flapping cube obviously reacts to the user input. When the user clicks, the cube goes up. And in order to react to this input, it needs to know that the input is coming there. So, and for now, as a placeholder, I will just define that flapping cube is the same thing as falling cube. And then I will change it here, so we can, when we write it, we can test our thing. Okay, this compiles. Okay, and again, to remind you, this thing, we can think of this behavior as of two stages. At first stage, the cube just falls down, and then when the event happens, we need to kind of generate the new falling cube function with some change state at which it go up. And let's just remember this thing for now. I'll just define this SF. I just leave it undefined for now. SF is this first stage behavior, and then I will define a cont, which would be a continuation, and it's the thing which creates the next behavior. So after the event happens, we need to create the new signal function, which would describe the new behavior. And the point is that we have this old one and something what would create a new one, and we need to just switch between them when the event happens. And Yampa provides us with this primitive or function, just a function, switch, which actually in the end we would use it this way: switch from signal function with continuation. And the type of the switch is, the type of the switch looks, oh, you can see it there, sorry. It's good now, right? Okay, the type of the switch is that, and I'll just paste it here. And you can see that switch takes this first argument, some signal function, and this second argument, some normal function, which returns a signal function, and then it results into signal function. But we actually use the switch here, so let's just put these types into our SF and cont. So first I will copy paste that, and I put it here, and this is our SF, and this is our cont. You can you? Okay. Yeah, that's good, sorry. And the end result is actually here, because we use the switch function here. So it's SF A to B. And let's just type check it. Yeah, it got compiled, because we use this undefined hack here, which just says, okay, let that be of any type. And now these types, just A, B, and C, are very generic, and I would like to specify them for our particular application in this function. So you can see that this expression is actually the final expression of the flapping cube function. So the type of this should be the same as this type, right? So we can conclude that A is an up input, and let me change it here and here, and B is a cube. Does it make sense? Okay. And well, now it kind of duplicates the information, so I'll remove this thing here. So again, to read it, we have some SF signal function from application input, and the output is a cube and some event C. And we have a continuation which takes that C value and returns a signal function from application input into cube. So the C value is something which is carried with an event, and it's this C value which is used to construct the new falling cube function. So when the event fires, this event passes something into the continuation, and the continuation comes up with a way to continue the cube behavior. So probably what it should be is that this continuation needs the last cube state in order to increase its velocity and produce a falling cube with a new state. And let's just say that C is a cube. So then continuation is taking a cube, and the cube has a position y and some velocity v, and the continuation is supposed to return a new signal function, which it would be switched to. And we can say that this new signal function is a flapping cube with a changed state. And the new state would have a cube with a same y position, right? When the click happens, the position of the cube is not changed. But what's changed is the velocity. And let's say that we increase the velocity by 300. So this continuation is what happens immediately after click. After click, we just take the cube and we increase its velocity by 300, and then we just restart a flapping cube with this new state. And now for signal function. So if we look at the type again, one more time, repetition should be good here. It has some input, application input, and then normally it returns a cube. It's like its normal return value, and notice that it's the return value of the whole thing. But alongside with a cube, it returns an event. So what switch does is that if there is event there, oh, I forgot to tell you about events. The event is actually quite simple. Any event is either an event with some value or no event. So if you know the maybe data type, it's actually the same. It's actually just or nothing. So, and when we have a signal function from something to event, it means that it's just a signal function which yields events. And any value of event can be either no event or event carrying some value with itself. So when the switch runs this SF signal function, it looks, does event fires at this particular sample? And if event doesn't fire, then it just returns what was the first output value, the cube, like the normal behavior. But if event fires, it takes what is carried with this event and passes this value into continuation. And then continuation comes up with a new signal function, and switch gets switched into that new signal function. And then it kind of transforms. Because notice that we have a recursive definition here. So when it switches to the new one, it kind of goes up, back again. Okay, now finally, after so many talking, let's implement this SF thing. And okay, input. I will use arrow notation again. Okay, to start with, normally, as I said before many times, it's a falling cube. So let's just first kind of run this falling cube thing, and we will do it this way, with initial cube and with some input. And then we also need to keep track of events of a user clicks. And for that, let's call this event flap. So when the flap event occurs, we flaps. And I would, it would be fed with input, and in the middle there would be a signal function called flap trigger, which I defined here. It as a signal function from application input to some empty event. This empty part, it's actually an empty tuple, a tuple with 0 values. So it's kind of unit, a value which carries nothing with itself. And this flap trigger occurs when either a mouse tap happens or a spacebar tap. So we kind of bin these two events and then we merge them together. We can add, for example, touch screen there and other stuff. And okay. And what we return in the end, we want to return, again, our return type should be cube and event cube. So we would return the cube, right? And then we return a flap event, but the flap by itself has, it has this type, empty event with a unit. But we want to return event which carries a cube state, and we tag this event. Tag is a Yampa's function with our cube state. Okay, this was just 6 lines of code, but it took me too much time probably to explain them. And let's just see if it works or not. I'll run it, and it's supposed, and yeah, it reacts when I press the mouse or when I press a spacebar. It kind of flaps up. I'm happy. So, any questions about these switching things?
Tag. What does the tag do?
Sorry?
The tag.
Oh, the tag. The tag, well, what I do here is just kind of an infix application. I could write it just this way. Tag flap with cube. Basically, tag takes an event A and a value B, and it returns an event B. So it takes event which carries some value, and it takes a new value, and it just tags this event with this new value and throws away the old one. So previously there was nothing there, nothing useful, and we just tag it with a useful cube state. Okay, so in fact we basically defined a whole cube behavior. Like, cube doesn't need to do anything else, it just needs to fall down and to bounce, to flap when we press a button. What's not defined is that when it goes down, it just goes through the ground, but what's supposed to happen is that the game should be over when it touches the ground or when it touches the pipe. But it's not really the job of the cube. I mean, the cube just falls down and doesn't care is there ground or not. We kind of want to observe the cube state and the game state from outside, and when the cube touches something, is it a pipe or is it a ground, we just say, sorry, game over. And or probably it's better to just restart the game, because just to keep the things simpler. And what I'll do here is I'll rename this game to a game session. And a game session is kind of like one run. So we have a game, our whole game, and it has the same type. And the game just starts a game session, then the game session goes on until something collides with something. And this means that game over, and the game is restarted with a new game session. And again, I would use the same switch here. I would later have some signal function, and I'll define a continuation here as a lambda function. Basically, it would be throwing away its argument. I just put an underscore here to say that I don't care about this input. And then it just starts a new game. So again, recursion here. And let me define a signal function, SF. So first of all, we are running a game session, right? So let's write a game session and bind its result to this game state. We again feed the input into the game session and then bind the result into a game state. What we want to do then is that we want to check, are there any collisions in this current game state? And if there are, then we emit an event and the switch switches into a new game. So we would call this event game over, and we would use this edge signal function, more on that later. And basically we would have a simple boolean check collision of a game state. So I will define a check collision a bit later, but its type would be a game to a bool. So check collision takes a game state and then it returns true if there are any collisions, and if there are no collisions and everything is alright, it returns false. What happens then is that this boolean value is fed into the edge function, and edge is defined in Yampa, and what it does is that it kind of listens, takes some boolean values, and if there is a true there, then it fires an event, and if it's false, then it's no event. And then we build this event to game over, and in the end we return our game state alongside with a game over event. And remember what switch does, it just runs this thing until event happens here, and in that case it just switches into that. So we can read it like normally.
What's the type of edge?
Oh, the type of edge. That's a good question. It's a signal function from a boolean to an empty event. So it takes booleans and emits events if there are true inputs. And I don't want to write check collisions now, so I'll just copy paste it from my old source, because it's like, it's not FRP, it's just geometry and some mathematics and some Haskell. So let it just be there. And I think that should be it. And let me try to run it. And if I run it and touch ground, the game restarts. Probably in the actual game we would want to make something nicer, like to write a game over, but I'm not concerned about this now. The point is that the game restarts. And notice that this check collision also handles collisions with pipes, which we don't need now, but we'll need very soon. And as the cube is now defined and cube collisions now defined, we can move into pipes, which would be kind of our last component. And let's just call this function moving pipe. It would be a signal function from anything to a pipe. Pipe doesn't really react to anything, it just moves, and sometimes bad things happen and a ball collides into it. But signal function of pipe doesn't know anything about the balls or the collision, so it just describes how the pipe moves. So, and for moving pipe we can do pretty much the same integrate thing, and it will look like that. I need to have some initial pipe state here, the same as with cube. So it would be pipe, initial position and initial height of the pipe. And the new position would be integral of -100. I just say that we move -100 pixels per second. Like the unit of time is 1 second, it's this kind of a speed. And when we integrate the speed, we get the position. And then I will add here the initial position and this cryptic operator, which we already know. A composition of a signal function and a pure function. And in the end we just return this pipe value with a new position and an old height. And then we will make use of it here. We would create a moving pipe with initial pipe state, and I would just feed empty input there. And if we run it, nothing happens again. I hate this. Let me just see what's wrong there. Any ideas? Probably I just forgot to reload the code.
Pipe.
Oh, I actually just forgot to reload the code. Nice. Okay, so the pipe moves. It moves. Oh, if we collide with it, we lose. That's nice. I forgot about this. But we can jump over. That's a cheating, but whatever. And the pipe moves, and then it disappears, and nothing appears because we haven't written that part of the game yet. So it's only one pipe. What we actually want is that when a pipe moves outside of the screen to the left, then we would kind of spawn a new pipe from the right. And let's guess how we would do that. Of course, we would do it with switch. So a switch okay, just define my signal function here, and the switch would be switching between a signal function and some continuation. And again, I would make a continuation a lambda function, and it would be recursing to the moving pipe with the same initial state as was given us, because for now all pipes are the same. And oh, I forgot to handle the events here. Actually, I need to define my event. I will call it respawn, the event which signals the switch. Hey, switch. And the respawn, I would use edge here again, because if the position is less than negative pipe width, then I want to respawn. And I will return this pipe alongside with a respawn event. And now if I run it, then the pipe goes on, disappears, and the new pipe appears. Okay, I pretty much can say that that's all the game for now, but it's kind of boring because, you know, all pipes are the same and not interesting to play. So the last thing I'll do before I go away is that I'll make these pipes to randomly generate the height. And well, I'll copy paste some code again. Basically, the only code which I'll copy paste is this pipe height generator, which is not really random, but let's just pretend that it is. And this pipe height generator is a signal function which doesn't really take any input, and it yields double values in this range. I just defined the range of suitable heights because we don't want the height to go too big. And we can make use of that pipe height generator here by putting the simplest way would be to put the pipe height generator in here and then apply the sequential arrow composition. And remember that signal functions are arrows, so if we have a sequential arrow composition, it's the same as sequential signal function composition. And notice that previously we didn't have any meaningful input inside our signal functions here, but now we actually do pass the height, the new heights there. So here I'll rename this inp into a new height. Previously we had h0 here, but now I will have h, like the new one. And when I have a respawn event, I will be tagging this respawn event with a new height of, so when the continuation creates the new pipe, I tell it the height of that pipe. And then I make use it in the continuation in this way. And this is supposed to work. Okay, not in mkstd gen is not in scope. That's because I didn't import it. So I import the system random this way, and I run it again. And okay, now it should be random. Probably I was just unlucky and it was at the same height. Yeah, I was unlucky. And now it generates a new one. And notice that every new pipe has a bit different height and they are in the correct range. So yeah, that was kind of the goal of the whole session. And probably we should stop now. Of course we can go and add some more features, but we're kind of limited in time. And that was probably enough. So before I finish, I don't know, probably it's worth to say of some kind of features which we see in that approach. And what I really like here is that you couldn't not notice that it's really declarative. Like, I just declared separate components. I pretty much could copy paste the physical formula and just put some parentheses and combinators there and it would work. And yeah, I just declare all things. I declare my kind of graphs and then they somehow get transformed into the behaviors which are rendered to the screen. I hope the next talk about implementation would touch on this. The integral thing is pretty interesting because, well, of course it doesn't do any symbolic manipulations, it simply can't, but it just samples the actual values. So when we render it, and we render it of course at a certain frame rate, which actually varies, every time it needs to emit the frame, it remembers the value and then adds them all together and gets this area under the curve in the end. And another thing I like is that it really composed of different pieces, because we have our game session, we just takes the cube from a flapping cube and the pipe from moving pipe, and neither flapping cube knows anything about the rest of the game, no moving pipe knows anything about it, and then it combines them together in the game state, and then we just check, is it everything all right with that game state, and if there are some collisions, we restart the game. So it's very, very encapsulated in that case. And the last thing is that normally when we are writing even such simple game, we would have a choice. We either keep the things at constant frame rate, or we keep track of our current frame rate and kind of change our accelerations and all our values according to the current frame rate. So if the user have a slow computer and he plays at 15 frames per second, the game would appear to him at approximately the same speed as a user with a fast computer. But here we do not mention frame rate anywhere at all. And in fact, this program would run approximately with the same speed at different frame rates. So it somehow gets adjusted. And this property comes from the fact that it's just a model of our game, and this model is continuous. So we can just pretty much take any time and render for that time. And then when we need to render, we pass the time deltas in there, and then the whole thing gets rendered. So yeah, that's pretty much it. And questions? Okay.
Could you quickly show the main program that runs this?
Oh, yeah, actually, and you reminded me about another thing called mini Yampa. And yeah, the main program, I actually have the main function here, but probably I would first show you the rendering function. The render takes our game state and it returns an object. It's just a normal Haskell function, and the object is kind of just a description of what the picture should look like. So we just have a bunch of rectangles here, like we say that the ground is a rectangle with a given dimensions and position and color, and the cube is another rectangle, and then we just put them all in the scene. Yeah, it's just a small kind of DSL which I define in this shapes file. So yeah, our object is, our shape is either a circle, a rectangle, or a scene with other objects. So we need that to just tell to the SDL thing what should it render without messing with I/O. And then I have a graphics model. A graphics model which actually renders the stuff. And here it has a render object thing, which takes an SDL renderer and an object. And if it's rectangle, it uses SDL render fill rect. If it's a scene is just a bunch of objects, it applies the render object to all of them. If it's a circle, then it uses this algorithm, which I had to write myself to render a circle. Unfortunately, I didn't use any circles here, which is sad. And our kind of main loop works as follows. Well, first of all, some SDL initialization goes. This function called animate, and I actually call it here in my main function. But here, SDL initialization go, we initialize it, we create a window, and then we create a renderer, and then we create some kind of mutable variable. Yes, you can have those in Haskell. And we create a mutable variable which is can be accessed from I/O and mutated, called last interaction, in which we store a time when we interacted for the last time. And then I just defined two local functions like sense input, which grabs the input, the user input from SDL, and the render output, which draws the output on the screen. And then I use the Yampa's function reactimate, which is kind of drives our main loop in the sense that it runs the sense input, which is I/O thing, gets some input, then feeds them into our signal function, and then the output of that signal function is rendered with render output. And then that's basically it. And in our main function, we call this animate function with some window name, dimensions, and then here we have that's what I was talking about when I said that. Can you see it? That arrow combinators are not as easy to read, because this is what they would look like even when we have 4 terms. So we first parse the window input. It's kind of that we transform those SDL events into our app input, which kind of more convenient data structure. And then we write our game. Remember, we were defining it here. And then we compose it with a pure render function, which transforms it into a bunch of shapes. And I also use this triple ampersand to handle the exit events. So when the exit event happens from SDL, you can see it. Anyway, we kind of exit. That's it. And another very cool thing is that this Yampa FRP, which somehow does the integration and other stuff, might seem quite complex, but in fact, it can be defined, or at least the subset which is used here, actually even more than it's used here, can be defined in just, 100 and something lines of code. That's basically it. You see that here it defines a new type signal function, and I wouldn't be going into details here because that's the topic of the next talk. I wouldn't spoil it. But the point is that we actually can change all our imports of FRP.yampa into the mini Yampa imports, and it would still work using this minimalistic Yampa implementation. But of course, I would also have to change it into the other files. Input mini Yampa. and I would change it in the graphics. Mini Yampa. And in shapes I do not use it. And let's try to build it. What else?
You left there this kg. Shapes.
Actually, no.
No?
Yeah, but then I removed them.
Okay.
The problem is in the... Oh, of course I have another model types, which is pretty much empty. Okay, now I changed all my occurrences of Yampa to mini Yampa. It compiled, that's a good sign. And it actually runs. And my CPU usage is a bit higher than it was with a Yampa implementation. It's here. But that's because, of course, this minimal implementation is not optimized. It's just written in the most straightforward way. But it could be optimized, probably. So, yeah, that was it for now. And the next talk would be more about implementation and how these things which I actually used here works, like the integration and switching, how they could be implemented. Okay, thank you.